Hey everyone, welcome to our next lecture on aromatic substitution reactions that have been what we've been leading up to by learning a bit more about benzene and other similar aromatic compounds. So when we talk about an aromatic substitution reaction, this has a few similarities to SN1 and SN2 that we already learned about earlier last unit, where one group is going to take the place of another group. So they have that in common, but there are a few things that they're going to be different in. When we do an aromatic substitution, we're going to have a very different mechanism. And we're also going to have some slightly different groups involved in the reaction. So clearly we're going to use something that's aromatic, and for our purposes basically always going to be benzene. But there is going to be a little bit of another difference when we were looking at SN1 and SN2 reactions. We always were trying to find a leaving group, but this time there's going to be no leaving group. So you won't be able to identify it by looking for a leaving group. We're actually going to have hydrogen is not going to be our leaving group, but it's going to be the thing that gets replaced. So we're replacing hydrogen. So instead of replacing our leaving group, we're replacing hydrogen instead. There's a specific name for this reaction that we are going to abbreviate as EAS, because that's much faster and shorter and nicer than saying electrophilic aromatic substitution. Whew. Yeah, so that's a mouthful. We'd rather just call it EAS. But we'll talk about why that E, A, and S come in when we start to talk about our mechanism. First things first, I want to introduce you to that mechanism and one of the EAS reactions called EAS bromination. So there are a bunch of different reactions that are all EAS type reactions that fall under this same category of being electrophilic, having this aromatic substitution happen under the same sort of mechanistic steps. So that's the EAS reaction is like an umbrella name that encompasses several reactions. We are going to learn about 5 of them this semester. And this is the first one where we'll demonstrate our mechanism as well. We'll learn about the rest of them at the end of lecture today. So here's our overall scheme. We start with a benzene ring here. I've drawn on one of those hydrogens just to show that that is what is going to be substituted out for at the end. We don't have that hydrogen anymore. We have a bromine atom. And it makes sense that we're going to get a bromine atom here because we're treating this with Br2, or that's elemental bromine, and this other thing, FeBr3. So that's kind of different and weird. Let's see if we can do what we've done in the past and just look at our molecules, look at what we're given over the arrow, and see if we can identify what roles they're going to play in the reaction itself. So if we look at benzene, that looked like a really good nucleophile, or is it our electrophile? I'm not really sure, so maybe let's skip over to the stuff over top of the arrow. But now we have a covalently bonded bromine molecule. It's not Br minus, right? That's different. Not sure. And FeBr3, I don't know. We've never seen iron before this semester. That's not really an organic element, right? It's a metal. So this one is maybe a little bit tricky to think about just at a face reading without having a little bit more explanation. So let's explain. One of the things that we talk about for the name of this is electrophilic, and the E in EAS is for electrophilic. So something has to be an electrophile, but we don't really know which part that is. So let's go ahead and compare this to something that we've seen that we are more familiar with by now. When we did addition of water or addition of HX to our alkenes, this is kind of more similar to what we're looking at above, right? Because when we had this reaction, we would get a carbocation formed, and we would then add, in this case, water, and by water I mean in the end product, an OH group, to one of the sides of that alkene, right? So it's a little bit the same in that we're substituting sort of like what would have just been one hydrogen here for now having an OH group, but that hydrogen is still in place, so it's not exactly the same. But we're adding something to that position. The big difference here is that we get to keep the pi bond in our EAS reactions. But that's the best analogy we have out of all of the reactions we've learned so far. So let's take a hint from these pieces of the reaction and see if we can't identify what is what. In our hydration of alkenes reaction, we had the acid here, right? Basically starts off the reaction as being a proton source, right? It acts as an H plus that we can pick up with our pi bond. And because this has no electrons to it whatsoever, it has to be our electrophile. So this stuff above the arrow helps us form our electrophile. And then in the very first step of the reaction, that pi bond has to reach out and grab that proton. So this pi bond is acting as our nucleophile. So if we take this and sort of try to map it onto our new reaction that we're learning about for the very first time, we'll see that the pieces can match up a little bit, right? So we have a pi bond here, right? And we want to pick the one that's adjacent to the hydrogen that we're substituting for, but there's our pi bond. That's going to be our nucleophile. So overall, the whole benzene molecule is going to be our nucleophile. And then the stuff over the arrow must be the electrophile. It's still a little bit weird seeing that FeBr3 here, but we'll talk more about what that does on the next slide. So we have our nucleophile, we have our electrophile, and then over the course of a few steps, specifically 3 steps, we're going to be able to make this molecule, which is called bromobenzene. So let's talk about those steps. It's 3 easy steps, I mean, easy for me to say, but I don't think they're too bad. Once you practice these 3 steps, you'll be able to do any of our EAS reactions, no problem. The first step is actually probably the hardest because this first step is different for each EAS reaction that you're going to learn. So what we have to do in the very first step is form a super electrophile. So why does it have to be super? Well, because I told y'all that benzene is special way back in the day, right? In fact, when we were learning this reaction here for the first time, someone asked, oh, which of the bonds on benzene do I use to hydrate as alkenes? And I said, oh, that's a great question, but they don't actually react because they're special, right? They have that extra stability that we talked about in the previous lecture. But that extra stability means that benzene's actually a pretty weak nucleophile. And if it's a weak nucleophile, then that means we need to give it some serious motivation to act in its capacity as a nucleophile. So that's why we want to make a super duper good electrophile. That way it'll be so reactive that benzene will have no choice but to reach out and act as a nucleophile. So we're going to form a super electrophile. In this step, it's going to be with bromine and FeBr3. Like I say, the other reactions will have different formations of electrophiles that we'll do all together at the end. But for this one, we have these 2 things and they have to react together. This is weird though, you would have never seen anything like this, but we can apply a little bit of what we know about nucleophile and electrophile to still figure out what's going to happen here. So the bromine itself has a whole bunch of lone pairs of electrons, right? As do all of these ones over here. I'm not going to draw all of them in on the FeBr3, but what about that iron? The iron is the weirdest and most different piece that we haven't seen so far yet. But what do we know about metals, just even from your general knowledge, right? They can be magnetic, and that they are going to form positive charged ions that we probably talked a bit about in Gen Chem, right? So even from last unit, when we were identifying our strong nucleophiles, things like these favorite SN2 type nucleophiles, they all had sodium, maybe potassium out front of them, and these all formed +1 ions, right? So that was the pattern that we looked at in the previous unit when we were finding our strong nucleophiles. And so even if you don't know anything about the transition metals, which you don't need to for this course, iron is also going to follow in that pattern of not being electronegative. It's very electropositive. It would rather become positively charged. So even if it doesn't have any kind of a formal charge on it, like we would see for a sodium ion, we know that this does have a partially positively charged character to it. So that being true, and these bromine atoms having all of these electrons around them, they're going to be attracted to one another just by the evidence of like charges attracting one another. So just like magnets, right? We're going to have the electrons on our bromine reach out and attack the iron. The iron has a bunch of available orbitals. You don't need to know anything about this. So it doesn't have to do anything. It doesn't have to lose any bromines, doesn't have to break any bonds. It can just make a new bond. This is going to happen reversibly because it can just be happening and unhappening all the time. So what we've created here is this kind of mashed up compound where we just sort of put the two pieces together, but we're not quite done drawing it yet because I'm missing a few things. We started out with two neutral molecules and we put them together and made some new bonds. So the charges are not going to be exactly the same. Think about this bromine here kind of in the middle between the iron and the other bromine. Bromine only likes to have one bond at a time. You've seen that every other place that we've drawn bromine out so far this whole semester. So if it has two bonds, it's not happy. It's sharing too many of its electrons and it doesn't like to share. So it has a positive charge on it. And iron, again, you wouldn't necessarily know this, but we gave it some new electrons, right? And that means that it has more than it used to, so it becomes negatively charged. Please be aware of these formal charges, even if you're not super sure where they're coming from. Make sure they get into your mechanisms, because anytime you are drawing a mechanism and you leave out a formal charge, it's going to be a little ding in points. But if you do it all the time, all of those points are going to add up to be a lot of points lost. So be careful with your formal charges, please. So we've made this thing here that's kind of weird looking. And this is our super electrophile. So what we've done here is basically take this whole group right here and turn that into a good leaving group. So what do you mean? How is that a good leaving group? Well, if that's our good leaving group, and just stick with me for a second, this piece here, this bromine, is our super electrophile. Why? Because when something comes in, our nucleophile is going to grab at this electrophile, right? It's going to come in from here. We'll draw this for real in a moment. The nucleophile is going to make a new bond to this bromine, and then that is going to force this bromine-bromine bond right here in the middle to break, which is going to be good because that will push these two electrons. Let me draw them in a different color here. Try to make them kind of purple so they stand out a little bit. It's going to force those two electrons to scoot over and go on to that bromine, thus neutralizing its positive charge. And that's going to be a good and favorable thing to do. So you're making this whole molecule here, but really only the last bromine atom is your super electrophile. The rest of it is just other stuff that we end up throwing away at the end of the reaction. But that's what we're trying to make here. So it's a quick little first step that we have to do to make our good super duper electrophile, and then we can actually bring the benzene in and start reacting. So now that we've made that great electrophile, let's go ahead and see what it's going to do with benzene. Step 2 is going to be to use our benzene nucleophile to form what we call a sigma complex. Your book maybe uses a different term for this. We'll get to that in a second. But we're going to make this new intermediate with our electrophile. So the nucleophile is going to react with the electrophile. And the arrows hopefully aren't too bad either. What we're going to do is use our nucleophilic pi bond. So that's these two electrons here. And then we're going to reach out and grab our electrophile. Remember, always starting at the electrons. Going over to here to grab our bromine atom. And then don't forget to draw that second arrow, which shows this bond here between the two bromines, breaking and scooting over to get rid of that positive charge on bromine. So when we do this, we form this thing called the sigma complex. Let me draw it out for you. I'm going to draw in this hydrogen on the adjacent carbon just to help us kind of keep track. So draw in as many hydrogens as you need to make sure that your brain is remembering where everything is. So there's our benzene-based piece. The other piece that we kind of don't care about is FeBr4 minus, right? Think about that piece. That was our leaving group. We got rid of the positive charge on this bromine atom, but the iron itself is still negatively charged. So that's a piece, it's just trash, we're gonna throw it away. You do not need to draw this into your mechanisms if you don't want to, but for those who like to remember where our atoms are all going, that's where they're going. But the other thing about this that's important to note is that if this is the iron with a negative charge, we have to have a positive charge somewhere to balance it out, right? Because we started with neutral benzene. This big crazy complex had some charges on it, but overall it was neutral. So we need to make this side of the equation overall neutral as well. And so that means that somewhere on this sigma complex molecule, we have to have a positive charge. So let's think about where that is. If we look at the top carbon where we're substituting, that's always a good place to start. But we have all 4 bonds to this carbon, right? If we think about that carbon atom, it has 2 bonds to other carbons on either side, and then it has a bond to hydrogen at the top and that bond to bromine. So that carbon is fine. It has all 4 of its bonds. It's happy. But what about this one adjacent to it that I just drew in? We think about what bonds it has. It has 2 bonds to carbon, 1 bond to hydrogen, but there's not another hydrogen there, right? Because go back to our original structure. Over here, it only has that 1 hydrogen. It used to have a pi bond, but when that pi bond was taken away to act as a nucleophile, it lost some of its electrons. So that carbon there that I've highlighted with that dot is the one that we want to have the positive charge on it. This can be a very tricky spot for students if you're working too fast. Make sure that the positive charge ends up next to where your bromine goes. It's not on the same carbon with the bromine. So now that we've finished drawing the structure of our sigma complex, you can see why the book calls this your carbocation intermediate, because that's a totally good name for it as well. We made a carbocation. We call this a sigma complex because we've ruined the pi bond here that we used to start. So you will hear me call it both things. Probably use whichever term makes the most sense to you. So this specific molecule here is our sigma complex, or carbocation intermediate. So one other thing to know about this step is that this step is our rate determining step or our rate limiting step. So why is that? What might be the cause of that? And so you don't have to know anything about rate laws or any kind of complicated math, but we do want to think back to our previous lecture where we talked about aromaticity. If we take a look at this sigma complex, I'm going to copy it back down here again for us. Let's do a quick little quiz. If we take this molecule here, is this sigma complex or carbocation intermediate? Answer the video question. Is it aromatic? Well, let's go through our steps, shall we? Our first step was to identify if it's in a ring. And yes, this started from benzene, so it was in a ring and it still is. There's some things hanging off of our ring, but it's fine. Is it a planar ring? Yep, it's 6 carbons, so it's definitely small enough. It will want to be planar, no problem. The trickiest part is just to see about all p orbitals. Do we have all p orbitals going all the way around our ring? And it looks like we're doing pretty good, right? Because we've got a pi bond here. Those 2 carbons are sp2, they're happy, they have a p orbital. Same with these 2 as well. What about this carbocation? We're happy with that because that is also sp2 hybridized and has a p orbital. But then we get to the place where we started to substitute and, oh no, that is going to be sp3 hybridized and it's just got too many bonds. There's no available p orbital there. So we can't quite aromatize this. So no, this is a non-aromatic compound. And so that's why step 2 is our rate determining step. Because what we started with, benzene, is happy and aromatic and nice and stable. But then we kind of ruined that. We kind of messed it all up to make this thing, a carbocation is already high in energy, but now it's a carbocation that just lost its stabilization energy from being aromatic. It's no longer aromatic and it's positively charged. So this is a very high energy intermediate. And there's nothing wrong with that, except that it just takes a lot of energy and more time to form. And that's why this is our rate determining step. But once we get to here, it's literally all downhill in energy, and so very easy to finish up with our last step of the mechanism. So the very last step of our mechanism is where we're going to make aromaticity happen again. We're going to bring it back. We're going to make it cool again. We're going to re-aromatize our ring by removing a hydrogen. So once we've done that, we will get back to aromaticity and we'll be happy. We'll be great. But there's a couple of questions that we need to consider as we're getting ready to draw this step of the mechanism. And those questions are as follows. Which hydrogen? I said remove a hydrogen, but which one? Does it matter? Yes, it matters. We only have one that we're going to be allowed to take off. We'll show which one that is in a second. The other question is what base to use, and depending on the reaction, there's going to be some different things available to you. So I will highlight the one that you're going to use for EAS bromination, and then I'll highlight the other ones as we go along and talk about the next reactions. So which hydrogen do I need? This is a very good question, and this is a place that I see students slip up. So do please be very careful while you're drawing and practicing these mechanisms. You see this one here that definitely I drew in for sort of bond counting purposes. And you say that one's right there. That's the one that I want. I need to remove that one. But actually, that's not the right one. We don't want that one. And why don't we want that one? Because it's right on that positive charge. If you think about this kind of like an E1 mechanism for this specific third step, we always needed to first form a carbocation, and then once we formed that carbocation, we had to look for our beta positions that had available hydrogens to them. So that's what we need to do here. We need to look at our beta positions. So this is kind of like an E1 style mechanism. If we go to our carbocation on the molecule and then go out one in every direction, we have two beta positions that are not identical. And one of them down here already has a pi bond to it. So we can't use that hydrogen because then we'd have like two pi bonds right next to each other. And that does not happen in a benzene ring. So this other one is our best bet as far as beta positions. And hey, look, it does have that hydrogen to it, right? The other reason that you know it has to be that hydrogen and that specific carbon position is because that's the one that's getting substituted for in our overall reaction. Let's go up and look at that scheme. If we think about this top position, this top carbon has one bond to hydrogen, but then that's gone in our product. So we know that hydrogen has to be the one that you're moving off, right? It's the one that you are substituting for, so it has to be the one that leaves. So make sure you always remove the hydrogen that you are substituting some other either atom or group for. And then what base to use? Again, it's going to depend on which reaction that you are looking at, but for EAS bromination, the base you want to use here is a Br minus. That's really the only basic thing that we have around because there's no water. You don't get to add anything else. You only use what I've given to you. So we're going to use a Br minus. It's not a good base, but it's the base that we have. So we're going to bring in that Br minus, like so, to remove our beta hydrogen. And then we're going to do this sort of E1 style mechanism that hopefully we're feeling pretty comfortable with by now, where we reach out with our base, pick up that proton. We want to go to the atom itself there. And then we want to take these CH electrons in that bond and let them fall down over here to kind of fill in our carbocation. And this is going to do the glorious, wonderful thing of also re-aromatizing our ring. So we fixed that positive charge. We now restored the sp2 nature all the way around the ring. So it's going to be aromatic again. And we were able to replace that, no offense, kind of boring hydrogen for something more interesting, like a bromine, that now we can do cool chemistry with. So that's the whole mechanism broken down into 3 steps. You're welcome to always draw out these 3 numbered steps while you're doing your mechanism, or you can kind of combine them into the traditional style mechanism that just sort of flows across the page. Whatever you want, as long as you get all of the steps in. Don't forget your formal charges, get your arrows drawn correctly. We'll all be good and happy. So let's go ahead and look at some of these other EAS reactions and start to identify their conditions. So like I said, there are a total of 5 different EAS reactions that we're going to learn about. And the first one you've already heard about, and that's the bromination we just did together. The other side of that is chlorination. If you want to chlorinate, you can do it in exactly the same way, exactly the same mechanism. You just have to replace all the bromines with chlorines. So when you want to do EAS bromination, you use Br2 and FeBr3. When you want to do chlorination, you simply have to use Cl2 and FeCl3. just like that. You might also see AlCl3 for aluminum trichloride. That works just as well. All right, let's talk about the next type. The next type of EAS reaction is a nitration reaction. So that takes benzene and puts an NO2 group on it. For nitration, you need nitric acid, or HNO3, and a little bit of sulfuric acid in there to help create our strong electrophile. But the nitro group, or the nitration, is going to come from that nitric acid. So let's look at the first step for that mechanism as far as how we create our strong electrophile. First things first, we start out with nitric acid. I'm going to draw that structure out for you here. We also need sulfuric acid, so I'm just going to draw out the first proton of that because we don't need the whole structure. We just need that first proton. The oxygen is going to pick that up. Don't forget to draw your second arrow and break that bond. And then that will be here in equilibrium, acid-base equilibrium, with this structure where now we have kind of a whole bunch of weird charges on our nitric acid. And we, of course, have the conjugate base of sulfuric acid that I'm not going to bother to draw in for us. But what these charges can do on nitric acid, we push down from that O, and then we kick out water as a good leaving group. So then we create this kind of funny looking thing, which is N2O, the positive charge there on that nitrogen. And again, there's water. That was our leaving group. So this nitrogen right here, that is going to be our super electrophile. That's the thing we're going to attack with our benzene ring. And by extension, we've also made water, and that's going to be able to act as our base in step 3. So be sure you're. The next reaction is called sulfonation. That means we're going to put an SO3H group on there, and it's going to make something kind of like a sulfuric acid, but instead of having the 2 OHs on either end, one is going to be a benzene ring. Sulfonation requires sulfuric acid, and we also need a little bit of SO3 gas in there, and we'll see why that is in a second. That's going to help us create our strong electrophile. So here we go. We're going to draw out sulfuric acid. We'll draw the whole thing out this time so that we can see the structure of it. Sulfuric acid is related to SO3 gas, that it's basically a hydrate of SO3 gas. So what we're going to do is use the SO3 gas to pick off one of these protons on sulfuric acid. Don't forget that second arrow. And then this will be in equilibrium with the deprotonated form of sulfuric acid. I'm just going to condense that down into its formula. And then here's the protonated version of SO3. And so this basically is just in resonance with a different resonance form. So we're not going to actually do any reactions or kick out any leaving groups for this one. We can just draw a resonance form that makes that sulfur positively charged, right? So that's all we've done is just moved a little pi bond around, and that makes sulfur our super strong and good electrophile. But then what do we use as our base? Well, we didn't kick out any water, so really the only thing that we still have around is our HSO4 minus conjugate base. So that's still around. We can just use that as our base for step 3. So there's 2 more EAS reactions that you now know how to make their electrophiles. Like I said, steps 2 and 3 are exactly the same for all of these mechanisms. So I encourage you to practice those on your own. I don't want to take up too much video time drawing them. You should work on them to make sure that you feel familiar with how to draw those arrows under each of these sets of conditions. But let's look at a couple more, our last 2 EAS reactions. This next one is called Friedel-Crafts alkylation. And so there's a lot to unpack there. The names Friedel and Crafts don't really mean anything chemically. They are named for the chemists who sort of discovered and optimized this reaction and made it famous. We also like to abbreviate this as FC. So if you prefer FC alkylation, you're welcome to write that instead. And you won't be really asked about the nomenclature of these reactions anyway, so don't worry too much about it. But then what does alkylation mean? Alkylation means that we're adding an alkyl group to our molecule. And what is an alkyl group? It's just boring carbon hydrogen, right? This is our alkanes. When it is a substitution on a benzene ring, we call it an alkyl group. So just going to be boring carbon and hydrogen. For our Friedel-Crafts alkylation, we start with some kind of a carbon-based chloride, right? So these R groups over here are any kind of R group as long as they're just boring singly bonded carbon and hydrogen. And then we also need AlCl3. So this mechanism will proceed much like we saw in the very first reaction because we used FeBr3 there. This works much the same. So let me just redraw this AlCl3 to make it look a little bit nicer. There we go. Okay, scoop that all down. And so in this first step to create our strong electrophile, what we're going to do is use these lone pair electrons on the chlorine. We're going to have those reach out kind of like we did with the bromine before, and that's going to form a new bond to aluminum. So this is going to be a bit like our bromination and chlorination mechanisms for this first part, where we're just going to form this kind of weird new complex where we have a positively charged halogen and a negatively charged metal. Take the electrons in that bond, scoot them over onto chlorine so that that whole AlCl4 piece basically just acts as our leaving group. And so there you have it. We've just created our strong super electrophile carbon, right? It's just a carbocation. We know those are electrophilic already. And then AlCl4 is basically going to allow us to make Cl-, and that's going to be the base that we get to use in step 3. And last but not least, we also have a Friedel-Crafts or an FC acylation reaction. So these names sound very similar. The reactions are a little bit different though. So if the names are kind of bumming you out and confusing you, just forget about the names and think more about the structure of what we're reacting with. In the alkylation, or the first version of this reaction, we just have a bunch of single bonds to our carbons and a chlorine there. Nothing sort of really interesting other than the chlorine itself. But when we do Friedel-Crafts acylation, we have what we call an acyl group. You don't really need to know what that means. It is this piece of our starting material here, and it has to have that C double bond O with a Cl coming off of it. So mechanistically, how does this reaction work? So again, I'm going to just redraw AlCl3 just to show all of the bonds a little bit more nicely. Same idea. The chlorine has lone pairs that we're going to donate to that aluminum to form a complex that looks a little something like this. And then we do something a little odd. We take the lone pair electrons on that oxygen, we bring them down to form another pi bond, and then we kick that chlorine out. So there's a couple different ways to draw this. I like to draw it this way to have sort of a motivation to kick out our leaving group. But we form this really funny looking thing there with a triple bond to the oxygen and a positive charge. That's called an acylium ion. You don't need to know how to spell that or anything. You just may hear me say it. So the carbon of that acylium ion, right? So I'm just highlighting it here to say that it's the carbon, not the oxygen, is the super electrophile here. And then of course, same thing as before, we have that chlorine. That's going to be our base for step 3. So now that we've learned all 5 types of EAS reactions that we're going to encounter this semester, let's do a little bit of practice. Some EAS PTP. So let's start with this first one here at the top. For pretty much all of these, we're just starting with benzene. So the key here is to identify which reaction we're doing based on the reagents and which group that will substitute onto our benzene ring. And then we just need to draw it on there. And because benzene is totally symmetric, you're welcome to draw that group coming in at any position. I'm usually going to draw it pointing toward the top of our ring, but it doesn't really matter for just benzene. So when we start off with this top one, HNO3 and H2SO4, the NO3 there should be your key that we're going to put on a nitro group. So we can go ahead and put that anywhere on our benzene ring. For PTP reactions, remember, you don't need to draw the entire mechanism. All I need is the product. So in that case, we make a nitrobenzene. Let's look at these next two, which based on their carbon containing electrophiles there over top of their arrows are going to be our Friedel-Crafts reactions. Since we didn't practice through the mechanism for any of these Friedel-Crafts reactions, you may not really be able to just see it super clearly in your head what the products will be. So let's just talk through these ones quickly together. We won't draw the full mechanism, but just to give us a little bit more of an idea. So when we make our good electrophile for this middle reaction here, we have this funny looking thing, the pi bond, right, with that Cl on the end of it. So when we have this, that means that we are going to make that funny acylium ion intermediate, which means that we're basically going to just chop this off. But then all the rest of what's left on the other side of my chop here is just going to get stuck onto our benzene ring. So when we go to predict the product for this one, we should know that this group, in combination with our AlCl3, means we're going to have a benzene ring with a Cl pi bond and some other carbons coming off of the end of it. Don't forget to number your carbons to make sure that you get them all. And again, you can draw this at any position on our benzene ring, but I just drew it off to the side to give us a little bit more room. Let's look at this third one. So we just did Friedel-Crafts acylation. This one, because it doesn't have that pi bond to oxygen here, it's just boring carbon groups that are all singly bonded. Nothing really super interesting. This is Friedel-Crafts alkylation. And that means we're just going to kind of put a boring R group onto our benzene ring. So whatever carbon you have attached to that chlorine is going to go onto our benzene ring like so. Again, counting your carbons if you're not sure. Just like so. So now that you're warmed up, go ahead and predict the product of this next reaction here at the top. Pause the video, decide what you think the product of this reaction will be, and then let's come back together and talk about it. If we're thinking about identifying what's happening with our reagents, we have Cl2 and AlCl3 that looks just like our bromination, except we're using chlorine instead. And again, it can be AlCl3 or FeCl3. Either of those work just as well for chlorination. So this means we're doing chlorination and we're going to put a Cl onto our benzene ring. There you have it. How'd that one go? Did you get it right? Let's try this next one. Pause the video, identify what you think is going to happen with these reagents, predict our product, and then let's talk about it together. We have H2SO4 in a couple of our EAS reactions, but when we see it in conjunction with SO3, we know that we are adding a sulfur atom to our benzene ring, and of course a bunch of those oxygens are going to come with it. So we are doing a sulfonation reaction, and that means we're getting an SO3H group added to the benzene. Just like so. Again, you can put it at any place on this benzene ring because there was nothing else there, so I just decided to put it kind of pointing down, just for fun. You should know, for the exam, the Lewis structure of SO3H. I may ask you that. Hint, hint. What about this last question? Let's take a look. We've got Br2 and FeBr3. So hopefully, because that's the one that we looked at first and we walked through that whole mechanism, you're feeling comfortable with that as being our bromination reaction conditions, where we're going to put a Br group onto the benzene. But now there's something a little bit different. I left a carbon on this benzene ring. So what do I do with that? When we talk about substitution reactions, there are a lot of different effects that come into play as far as where you would substitute on a benzene ring that already has some groups on it. We don't have time to get into a whole lot of that this semester. So suffice it to say, if you have a group sticking off of your benzene ring and you're going to try to do one of these reactions to it, any of our EAS reactions, what you want to do is just put that group as far away from the first group as you possibly can. The reason for this has to do a little bit with some of the resonance forms. Again, we don't have time to get into that. But the other thing, the way you can think about it is that if you have some group already on your benzene ring, even here it's just a methyl group, but we don't want to get close to that because it's just hard to get in close to that methyl group, especially if it was anything bigger and sort of branchier or more crowded. We would just much rather go to the furthest away position that we can get. The furthest away position that we can get is down here at the very bottom. So whenever you get a reaction like this, you want to just put that new group as far away from the first group as you possibly can. So all the way across the ring. So that means we have that methyl group there. Always double check your carbon count, make sure you don't drop any carbons. But then the bromine is just going to want to go as far away from that methyl group as possible. So there's a little bit of practice with our predict the products reactions for EAS. Now let's think about what else we need to practice and review. So we want to think back to identifying aromaticity again, right? So we did a little bit of practice with that when we talked about the sigma complex today, but that will definitely be a big portion of our exam is identifying the aromaticity, anti-aromaticity, or non-aromaticity of a variety of compounds. And then you want to be able to identify our EAS reactions and be able to tell them apart which one is which. So you need to know the difference between sulfonation and nitration. You need to know the difference between Friedel-Crafts alkylation and acylation. Even if you don't worry about having to spell those words out, just be able to identify the difference between them and be able to draw their mechanisms correctly. Okay, so that's the other piece here, that we need to be able to draw those EAS mechanisms for all of these. Like I said, I did not draw out a bunch of these EAS reactions because steps 2 and 3 are very much the same. So what you should do is take all of those first step things that we did say on this slide and the previous slide here, where we showed how we make our super electrophile, practice redrawing this, and then do steps 2 and 3 for each of these reactions as good practice. And then if this is all feeling good and fine, you can start looking ahead to carbonyl chemistry. So what the heck is carbonyl chemistry? You probably never heard that before, but that is the name for the functional group when we have a CO pi bond. That is a carbonyl. And there's a bunch of other different functional group names that we'll talk about in the last portion of this unit. So if you have any questions about either aromaticity, EAS, or mechanism drawing, please let me know. You can leave a comment here. You can leave a comment in our discussion forums. You can send me an email, or you can always drop by office hours. Office hours are Tuesday morning from 10 to 12 or Wednesday afternoon at 1 to 3. If those times don't work for you, send me an email. We can set up a separate session. Just let me know. Until then, everybody have a safe week. Take care.